Okay, relative dating. This is all about saying what came first, whether it's a geologic event or the deposition of a sedimentary layer, just saying this came before that. The idea is that you can determine the relationships through a couple of principles, and we'll go through those. Stratigraphy, couple terms here. Stratigraphy is the description, correlation, and classification of strata layers of sedimentary rocks. In geology, you can have a whole class that you take in your major called stratigraphy, and it's figuring out how one layer relates to another and describing the geology of those layers. The principle of original horizontality. Sediments are deposited in flat-lying beds, and those beds are one on top of another, and so they are found horizontal. If they're not horizontal, if something has folded or tilted them, usually plate tectonics, then we would say they've been deformed. They're no longer following the principle of original horizontality. So here are beds that are one after another. The oldest one's on the bottom, youngest is on top, and they're that flat-lying original horizontality. They're undisturbed. Cross-cutting relationships is another principle where we can say that an event or an event that changes a rock has to be younger than the rock that gets changed. And that change can be things like folding, faulting, intrusions. Those are all going to happen after the original rock was deposited or formed. So cross-cutting relationships. So in the image, there's that dark gray background rock. We call that the country rock. It's been cut through by this light colored granitic dike, and then both of those have been cut through by this dark dike. So there's three rock types: the oldest gray background, the middle-aged is this white granite, and then it's cut through by what appears to be a basalt. So I don't know the exact ages of those rocks, but I know which one happened first of the three. Okay, principle of superposition. That's that idea that the oldest rock unit is on the bottom and the youngest rock unit is on the top. So that's in an undisturbed sequence. Sometimes rocks get flipped upside down, but in an undisturbed sequence, the oldest is on the bottom and the youngest is on top. So here's, we look at sometimes fossils to think about the time from evolution from one fossil to another in that sequence. So this order here is the stratigraphic order of those units. The deposition, though, of these sediments is not always at a constant rate. Think of, let's talk about that rate for a second, a flood deposit. Say there's a flood on a river in your town. There may be sediments that are deposited on the floodplain instantaneously that day. Those are flood deposits. So the rate is maybe a foot of sediment per day. That's a lot of sediment. The rate of deposition of clays, so tiny little particles in the deep ocean for just a centimeter of sediment could be 1,000 years. So the deposition rate is not constant. And there are times when there's no deposition. So look beside you. Is there deposition? No. So there's no deposition sometimes. River channels move. So maybe there was some deposition in a river channel, but it's moved and now it's eroded some of that evidence and there's no deposition at that time. Sea level also rises and falls for different reasons, mostly related to changes in climate. So we have sea level rising and falling. If you go to just outside of Raleigh, down I-40 in North Carolina, you can find marine deposits, sands. So there, the ocean was up where, like close to Raleigh, 20,000 years ago. So sea level changes. And right now in Raleigh, there's no marine deposition, right? There's no ocean there. But out on throughout the coastal plain, there's not a lot of deposition. But when you get to the beach, our barrier islands, there's deposition again. So there's erosion right now all across North Carolina, not deposition. So plate tectonics can create basins and closed basins, which changes sedimentation rates and where sediments are being deposited. So what was deposited can easily be eroded away and not preserved in the first place. So in a stratigraphic column, you're just going to have the rocks that were in rock units that were preserved. Some of them are going to have eroded away and not be there. When you have gaps in the rock record where there's no deposition or the rocks have eroded away, we call that gap an unconformity. We'll talk more about unconformities, but those are unconformities where we have gaps in the rock record. Because of these unconformities and the lack of deposition in some areas and deposition in other areas, sometimes it's difficult to correlate rock units across great distances. Fossils then can supply some of that missing information about the age of rocks and also how to correlate one rock unit to another. Fossils can help us do that. They help us recognize missing time and think about those gaps in the geologic record. Some of the fossils are called index fossils, and those are fossils that we know the age of, and we can use those to narrow down the age of rocks. So we're still talking about relative dating here, but we can know the age of those fossils. Okay, that looks like this. Here at the bottom. It's called faunal succession, where this is a trilobite and then other bivalves, and there's a T-Rex, and here's a maple leaf and a starfish and a bryozoan. We can look at their age range and where they overlap and start to determine, when we find a range of fossils in a rock, what the age is. Some fossils are called trace fossils, and those are just fossils that are impressions of like animal tracks. Some fossils are shells. We have teeth, bones, plant impressions, worm tunnels. Studying fossils is called paleontology, so you could be a paleontologist as your job, and they work out that fossil record and study the morphology of fossils. Let's see. So paleontology has helped geologists work out the geologic time scale for the world and stratigraphic relationships. In 1859, when Charles Darwin proposed the theory of evolution, it kind of changed the idea of paleontology and really made it, let's realize it was just a really useful tool with that faunal succession and overlapping of fossil ages. There are different ways that fossils can be preserved. So let's look at some of those. You can actually preserve the hard parts of seashells. So in this image, those are some kind of bivalve, and we've preserved the actual shell. Bones. So we usually think of dinosaur bones, but fish bones, and then mammals, the early mammals, we can also preserve their bones. So bones of any kind can be preserved. Replacement. This is the stump of an petrified wood, and when that tree was alive, it was bringing into the cells silica-rich water, and when the tree died, it was in water, and the silica had replaced the cells, and so now we have that preserved stump. It's petrified wood, which is like a siliceous wood now. Castor mold, this is just to be the impression of a shell. So this is just in that limestone. It's like taking a shell and pushing it into Play-Doh. Now we have just the mold of it. We can have thin films of material. So this mostly with leaves, and also the impression of fish. So the fish is no longer there, but in that really fine-grained mud, it's left the impression of it. Amber is tree sap that is hardened, and here it's hardened around some, looks like little gnats or bugs. And constructed features. So constructed features would be something like a preserved coral reef. This example is a stromatolite, which are algal mounds. They're some of the oldest life on Earth. Oh, is that covering up that word? Sorry about that. So fossils. Okay, back to those unconformities. These are those layers that represent the missing time. And in a block diagram like this, it's always going to be that wavy line there is the unconformity. So where a formation is missing, a formation is the mappable rock unit, where it's missing from expected stratigraphy, the layering, a geologist will try to explain what has happened, and it's going to be either that was a time of no deposition or that formation eroded away. Either way, there's missing time in the rock record. We call that an unconformity. And it's that layer, that boundary is that missing time. And there are three kinds: an angular unconformity, a disconformity, and a nonconformity. So let's look at this unconformity here put my face in front of that. In the first block here, here's a deposition of a gray limestone. Later, that gray limestone was folded. So I took one limestone and now I folded it, and it's been eroded by rivers. And now we have deposition of those river gravels on top of the limestone that was folded. So now, like Cigar Point, this is an angular unconformity where the limestone's at an angle and the flat-lying river gravels are on top of it. So that's one kind. That's an angular unconformity. Here is the nonconformity. So we have a chunk of rock here. This would be a crystalline rock, either metamorphic or igneous, not sedimentary. And then here's some gravels being deposited on top of that surface, and that would be then the nonconformity between an igneous or metamorphic rock and a sedimentary rock. So an example of this would be like the coast of Maine, where the mountains are right up next to the sea. Those mountains are metamorphic rocks like schist, but there's also granites in those rocks. If you've ever seen pictures or been to like Acadia National Park, those are granites. And then the Atlantic Ocean is right there at those granites, depositing sand on top of that granite. Well, that granite is an intrusive igneous rock that formed deep underground. It is now exposed at the Earth's surface through plate tectonics and erosion and time, and now sand is deposited right on top of those old granites. That's a nonconformity. So here's an example of what that looks like. Precambrian granite, really old granite, and then on top of that, Paleozoic sandstone. So there's millions of years of missing time between the formation of that really old granite and then the deposition of that sandstone on top of it. Okay, last one. This is the disconformity. And a disconformity, we're going to start out like we did with the angular unconformity, horizontal layers of limestone, and then over time, if the sea level drops, then it's going to expose that limestone to erosion. So this is the weathering, eroded surface of the limestone. Time passes, la 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 la. And then sea level rises again. My face is in the way. Sea level rises again. More limestone is being deposited, but there's that missing time. It's representative of this erosional surface here. That's the disconformity, where old limestone was eroded as sea level dropped, and then as sea level came back up, now new limestone is being deposited on top of that disconformity. These are harder to recognize, right? Because we have flatline sediments and flatline sediments. What you really would need is to recognize the erosional surface, maybe some pitting in that limestone, or the fossil record in those limestones. So perhaps there's fossils in there that you would know we're not one right after another in the sequence. Something may be missing in that stratigraphy. Okay, here's an example of what we would look at. Turn my face off. All right, time number 1, these sediments are forming in an ocean basin. Always those blue blocks mean water. So beneath the sea, sediments are accumulated in beds. Time 2, later tectonic forces cause uplift, folding, and deformation of the sedimentary layers during mountain building. So something acted upon these rocks to make them no longer horizontal. They're now in anticlines, that's what we call that, and synclines, these folds, anticlines and synclines and anticlines. And they've been now eroded by this river. Okay, this would be like what we see in eastern Tennessee. Limestones and shales and sandstones that are folded and then cut by rivers. Eastern Tennessee rocks. Time 3, now we have some magma activity. There's a pluton beneath the surface shooting off dikes, molten rock into those folded sedimentary rocks. Time 4, we're squeezing those units and we've cut through the folded sediments as well as the dike. So now the dike has been cut. So when a geologist sees a block diagram like this, we try to see what's the last thing that happened and can we work backwards to determine the sequence of events. All right, when you figure out the geology of an area like that, you can make a geologic map. This is the first geologic map ever made of a region, and it was made by William Smith in England, and he produced the map, this geologic map, at a time when there wasn't really an understanding that one rock unit could be regionally found, from the north to the south. So he realized they were the same, marked them on a map, and made these connections that this yellow unit weren't clear across the country, right? There's a book about it if you're interested in the history of science called The Map That Changed the World. It's a really good biography of William Smith from 1815. Okay, so that's the first geologic map. Here's another geologic map. This is a geologic map of just a zoom in on the Grand Canyon. And I show this so that you have an understanding of what a geologist does. So a geologist will walk around the Grand Canyon, putting this information on a topographic base. So this corner here shows the topographic lines. Each color on here represents a different rock unit. So all the purple is one rock unit, all the greens, one rock unit. The blues and greens are sedimentary rocks, and the oranges are crystalline rocks like metamorphic rocks. There's the Vishnu schist and igneous. There's the Zoroaster granite in the inner gorge down here by the Colorado River. So this is a geologic map of the Grand Canyon. Let's look now at North Carolina. So here's that word, formation. These are the mappable rock units. So for North Carolina, we have our coastal plain, younger, mostly sedimentary rocks. And then we go into the squished up, messed up Piedmont. So these are Piedmont rocks. And then this line here is the Brevard Zone. And the rocks on this side of the Brevard Zone are older. These are thrust sheets where we've got one fault has moved. Many faults have moved rocks all on top of one another and stacked up these different thrust faults in the Blue Ridge Mountains. Brevard Zone, squished up rocks of the Piedmont, and then this marks the edge of the coastal plain for North Carolina. So that's the geology of North Carolina.